So it's a pleasure to welcome the talk of Alcides Buss from Federal University of Santa Catarina in Brazil, who will speak about amenable actions of groups on sister algebras. Alcides?
Okay, thank you, Guillermo. Thank you for all the organizers for the invitation. So, as you see in the slides, I'm going to talk about the many actions of groups on sister algebras. Let's go to the second slide. So there you also see
Wait.
the,
Now I have, wait a second.
on the second,
Yeah.
I just reviewed the abstract that's also available in the homepage. And there, so you see, based on mainly on joint work with Siegfried Eckerhoff and Rufus Willett, at the very end, I also talk at least about one result and another joint work with Fernando Abadi and Damian Ferraro. Okay, let's go to the next slide.
Yes.
So I'll start with the classical notion of amenability for groups. Yeah? So for the whole talk, I'll be fixing G will be a locally compact group. Sometimes it will be discrete. Yeah. Let's go a bit further. Yeah. So one of the classical definitions, this is the usual classical definition of amenability for groups, one requires a G invariant state on L infinity functions on G. And if you go a bit further, I recall the action that's being used there. It's the left translation action. You could also use the right translation action, would be equivalent. But we also are fixing this very important action for the whole talk. And the next slide, I recall some of the 1,000 different characterizations of amenability for groups, and recalling the most important ones for this talk. And so the first one says that amenable, if and only if there is an approximative net in the sense of almost invariant vectors in L2, you can also replace this L2 condition there by which is converging to 1 by saying that these things there really are almost invariant in the most obvious sense in the L2 norm. And also you can write these functions there. If you look at these bracket functions, these inner product functions that are being defined in 2, and you call them theta. So these are the positive type functions. Essentially, every positive type functions with compact support is essentially of this form. And this gives the equivalence with 3. And this is essentially a way to say also that the left regular representation is weakly contained in the trivial representation of the group. And maybe the most interesting condition for sister algebras is saying also the group is amenable if and only if the full and the reduced group sister algebras are the same. And in addition, if the group is discrete, then also one can relate nuclearity in the sister algebra case or injectivity in the von Neumann algebra case, which are notions of amenability in the sister or von Neumann algebra level. Yeah? So this fits nicely with all these issues. So let's go to the next slide, Willie. So once we know amenability, so I didn't give examples, or you know many examples, amenable, so like abelian, solvable groups, but there are many groups which are not amenable, like free groups, but still they do have some amenable action. And then this notion of amenability is also contained in the book of Claire, Nathalie de la Roche, and Jean Renaud, about amenable groupoids also fits in this picture, anyway, so amenable actions here in this sense can be defined in this way. You can you find a net of functions of map from X to measures, to probability measures on G. And there you can also consider the translation action, and which is being used in this condition. And then we require a sort of equivariance, almost equivariance in this condition. So the idea is that in some limit of this net, we find also, like for amenable groups, some invariant thing in the limit. So this is a notion of amenability for actions of groups on spaces. Yeah? So then the next slide. We are going to use a lot exact groups, and then this relates nicely to amenability. And so I don't know, probably most of you already know the definition. I didn't give the definition of exact groups, but you can think of this result as being one definition. So the group is exact if and only if it admits an amenable action on some compact space. And we can replace this one compact space by the sort of universal one, which is the spectrum of the uniformly continuous functions on G, again endowed with the left translation action. Yeah? So in the case of discrete groups, this uniformly, every function is continuous, uniformly continuous, of course, and then we get the Stone-Check compactification as the spectrum. And in this case, it's also known to, exactness of the group is known to be equivalent to C star exactness of the group C star, the reduced group C star algebra. In general, we don't know. So many examples like free groups and more generally parabolic groups. Also, this next slide, almost connected, locally compact groups. Many examples. Many groups are indeed exact, and a few examples we know of non-exact groups like the Gromov-Monster groups. They do exist also. Okay, this is about exactness. And now let's move to the non-commutative words, the seminar about non-commutative geometry. So let's now go to sister algebras. So our desire is to also go beyond the spaces, commutatives, the commutatives sister algebras, and we want to consider more generally actions on sister algebras. And then let me just recall the most important objects that we can assign to an action, which is first the full cross product, and second the reduced cross product. And I'm also recalling that both can be realized as completions of the so-called algebraic cross product, which is concretely the space of continuous compactly supported functions endowed with the convolution. And then the main question here is for this talk is when they are equal. So when these both norms that we have to complete, then when they coincide. This I'm be referring to this as the weak containment property, when these norms and then the cross products are the same. Yeah? So, and as we learned from amenability of groups, this characterizes amenability of groups. In the case of groups, full and reduced being the same is equivalent. And then we are going to talk exactly about this later. Yeah? We believe that this should be some sort of amenability, but then, yeah, go to the next slide, please. And the question is then, what is amenability? And now, of course, then we want to relate this to amenability of actions. The thing is that for sister algebras, if you go directly and want to define this somehow in an obvious way, this gets complicated and doesn't work. But if you go a bit further and jump to von Neumann algebras, then actually there things are very similar to the amenability of groups. So you see in the definition, this is definition from more than 40 years ago now, by Claire, also Natajama de la Roche. She defined in 1979 a notion of amenable actions on von Neumann algebras. And there it's essentially the same if you just add the coefficient m is the von Neumann algebra. Instead of requiring a state, you require the existence of a projection or equivalent a UCP map or projection or condition expectation. You could also say this map P, which is there, is the generalization of this state, yeah? And then of course you replace the invariance by the G equivariance, and this is then the natural definition of amenability, and this is what Claire uses as the definition. We use now here the action, of course, on M, and also we use also the translation action on G is behind there in this definition, you see. So let's move to the next slide. She proves then a bit later, in this paper already from 79, she proves some results. Then she has another paper from, I think, 81. And a bit later in 87, she proved what is the most important, one of the most important results for us here. So first, she proves, I think this result for the center is already from 81, but anyway, she proves that this phenomenon, this amenability for von Neumann algebra is actually not a non-commutative phenomenon. It's actually just amenability for the center of the algebra. So in this sense, amenability is just a commutative phenomenon actually in the level of von Neumann algebras. And also she proves a characterization of amenability, but now only for discrete groups. Yeah? She could prove these approximation properties for amenability, like we have for amenable groups. We can approximate this map P actually by these functions, these nets here. So of course we need to put coefficients suitably here. Instead of L2 functions, we take L2 maps into M and consider this as a module over M. And essentially the rest is essentially the same. Of course, we have, instead of convergence, the usual convergence, we should use here the weak convergence, the weak star convergence, or ultra weak convergence is always the same here. The nets are bounded. And also one can rewrite these in terms of positive type functions, but one has to add the action. So we say the positive type functions with respect to the action. But essentially the same, in the same spirit as for amenable groups. And also she proves that this behaves nicely with injectivity of von Neumann algebras. So if the von Neumann algebra is injective, so some people say amenable also, then the action is amenable if and only if the cross product is injective. Yeah? So this is a very nice result. So now the question is, what happens now to C-star algebras? So in the next slide, I explained, so also Claire in the same paper, she proposes a definition in that case, but again, only for discrete groups. So she says that she uses the natural route that one usually does for going from C-star to double star algebras. Yeah? What one can always do is take the C-star algebra and go to the bidual. Yeah? The bidual is always a von Neumann algebra, we know. And then if the algebra carries an action, the bidual carries an induced action. And in this case, we don't have any continuity. So this action is, in the discrete case, we have a nice von Neumann algebra action. And she just says, so the sister action is amenable, is this double dual action is amenable as a von Neumann algebra action. So then just recalling this means then there is this projection or there is these nets that you can build to approximate this projection. Yeah, it's just a restatement of this result that she proved. Okay, let's go to the next slide. And then she also proves this important result on the C-star level that says that when the group is discrete, if the action is amenable, then we have the weak containment property. So the full and the reduced cross products are the same. So this gives already an answer, at least a sufficient condition for the weak containment. And also she relates this with nuclearity. It's a very nice result also that says that when the algebra is nuclear, then the action is amenable exactly when the cross product is nuclear. So this fits very nicely with a nuclearity, this notion. Okay, and then the next slide, now I have a question which is still open today in this setting, which is the question whether the converse holds, whether the weak containment implies amenability. We only know the converse, so this direction is still open today for discrete groups. We are going to give a partial answer later. So let's go to the next slide. It will appear actually already a partial answer was given by Matsumura in 2014 for this question. So, so he needs to assume the algebras to be unital and nuclear always. Then, and also more assumptions are coming. There are two cases. First, in both cases, the group is exact, needs to be exact. Yeah. In the case that the algebra is commutative, unital. Yeah. Also, he proves that this question has a solution. So the weak containment implies amenability. So both are equivalent in the commutative case, and they are equivalent to topological amenability, is also known. And in the non-commutative case, he could not prove that the same result, unfortunately. But, yeah. And in the non-commutative case, sorry, I think there was some problem with the sound. So in the non-commutative case, he could prove at least a version of this. One has to incorporate, we don't know whether the same result holds in this case, but what we can prove, what he could prove is that if one looks at the tensor product of the original action with the opposite action. So we take A tensor A op and then asks for the weak containment of this action. This is equivalent to amenability of the original action. This is what we can prove. Yeah? This is Matsumura's theorem. Okay, let's move on. So now the question, the next natural question is what happens now for locally compact groups? All these results in the sister algebra case are only for discrete groups. So, and this is the main problem. If you just consider the bidual, it's still a von Neumann algebra, but the action there need not be continuous in the von Neumann algebra sense. So it's not weak star, pointwise weak star continuous as it should. So it's not a von Neumann algebra action. And the problems already appear in the most basic example like C0 of G. If you consider C0 of G, the bidual is too big. So it contains, for instance, all bounded measurable functions, and the dual contains all the duo of this algebra contains all the measures, in particular the direct measures. So these measures and the points, they make this action not continuous in the natural way. So this is not a good action. It's not a von Neumann algebra action. Then one has the question, can we replace this bidual by something else? And then this is the answer. So we first proved without knowing that this was already known before. And after we proved this result, we discovered from another paper by Biardin Crane that this result was already known by Ikunishi. So, but at the end, we have then two constructions, two proofs of this result, which is states that there is a nice von Neumann algebra always attached to an action of the sister algebra. So the point is, for every action, there is a unique up to isomorphism of von Neumann algebra with an action, a von Neumann algebra action, which has this universal property stated there. Every morphism in this from actions from A to a von Neumann algebra extends to this von Neumann algebra in a normal way, a von Neumann algebra morphism. So of course, this is a universal property that characterizes the algebra. So what Ikonishi does is he essentially replaced the dual by a smaller subspace. He only considers the continuous part of the dual. Here I mean continuous means for the norm topology. You induce, you have the action, and then you induce the action on the dual, and then you can talk about the continuous elements for this action. This is what is meant in this there. And then what he does is he realizes this as the pre-dual of some von Neumann algebra, and this is this von Neumann algebra of the statement. And our construction is slightly different. We don't look at the dual, we look at the cross product directly. We look at the cross product of the original action, and then from the cross product, we look at the bidual of the cross product. Of course, this is a very huge object, but there we have a lot of information. The action, for instance, in the cross product, you can realize essentially as an inner action, at least in the multiply algebra. And you can embed the algebra inside the multiply algebra, and then the action in the cross product is given by as a joint action by some unitary representation. And this is the point here, because being inner the action, then the bidual is still nice. So, and then what we do is we look at the image of the bidual of A inside the bidual of the cross product. Yeah, and this image is this von Neumann algebra. In general, this map from the bidual of A to the bidual of the cross product is not injective. That's the problem. In the discrete case, it does. It is injective. So in this case, it is the usual bidual, but in general, this new von Neumann algebra is just a quotient of the bidual, a smaller quotient, as we saw in the example. If we go to the next slide, I revisit this example. So we look again at C naught of G. And in this case, if you look at the dual, you get all the measures, all Borel measures essentially. And you should only look at the continuous part, you take only the L1 functions, view it as measures, say. And therefore, the dual of that is the L infinity. So this is the Ikonishi's point of view. If we go to the cross product, we can get the same. In this case, we can compute the cross product is the compact operators. So the bidual of the compact operators are all the bounded operators, and the image of the C0 of G, the double duo, or just the von Neumann algebra generated by C0G is just L infinity. So we get the same from both pictures. So this is indeed, should be the correct algebra in this case, the L infinity, not this big double duo. So, okay, and then now we follow the same pattern essentially as Claire did for discrete groups, except that we replace the double duo by this new von Neumann algebra. And then essentially all other things are essentially the same. Of course, we need to take care of continuity here in the locally compact case. So we require, for instance, amenability. We use this, one of these characterizations by Claire to define amenability in terms of positive type functions or in terms of L2 functions is the same. So we require a net as before, but now of course we need continuity, and also we need to take continuous part in the center as before, as in Claire's theorem. And this net should also converge to 1 as before weakly, but now also we have to add uniformly on compacts. But this also turns out to be not very important, but it's essentially the same thing, except that we add continuity and uniform convergence. Okay. And of course, the remark here is just the continuous part as before. We take the non-continuous part of this von Neumann algebra for the action. Okay, this is our notion of amenability. Of course, we want now to relate this to other notions of amenability. Another obvious notion, which was available already before, is this stronger notion of amenability, which we call strong amenability. Instead of, we can forget everything about this von Neumann algebras. We can just stay in the algebra. But instead of looking at this von Neumann algebra, we just take essentially the center. The center might be too small. We go to the center of this multiply algebra. Yeah? And then we take continuous part and we play the same game essentially. We take positive type functions with the same conditions, except now instead of weak conversions, we take strict conversions. If the algebra is unity, of course, this is just non-convergence. Yeah? This is a notion of strong amenability. It's easy to see that this implies amenability in the previous sense, and also not difficult to see that this notion of amenability coincides with topological amenability in the commutative case. Okay, but this is really stronger in general. We are going to come back to this soon. So, and this is one of the many results that we have put together in one statement here about amenability. Yeah? It's a characterization of amenability. Unfortunately, we need to assume the group here to be exact to start. And this is really, in this statement, this whole statement is necessary. But let's go. So if the group is exact, but now locally compact, we can prove that this notion, this new notion of amenability that we introduced is the same as this definition by Claire from 40 years ago in the level of von Neumann algebras. If we go to this universal von Neumann algebra, we can also prove that this is equivalent to strong amenability in the exact case, to strong amenability of the continuous part of this von Neumann algebra. Yeah, it's a very huge object, still very huge, and but it's equivalent to strong amenability. So of course, this means also topological amenability of the spectrum of the center of this algebra. Yeah, as I said before. And we also give other conditions, like these conditions. There is a map, a suitable map, a UCP map that is compatible with the action from L infinity to the center. And also we can replace this by a map coming from this space of uniformly bounded continuous functions to the center of the continuous part. This is a condition that might be easier to check, of course, this existence of such a map instead of existence of some net. It's a condition that you might check in many cases and just say, oh, we have such a map and then the action is amenable. And also we proved this non-commutative version of Matsumura's theorem, which is exactly the same, but we remove the nuclearity assumption and also the unitality condition on the algebra. We remove every other assumption except for the exactness of the group that we still need to keep. And the result is essentially the same, but we use the maximal tensor product here because we don't have nuclear sister algebra, and this fits with the proof. The proof is essentially the same idea of matsumuras and uses Hagerup standard form, which gives a special representation which incorporates the algebra and its opposite algebra in the same place. This is the main ingredient. Maybe I have some ideas for the proof, but I don't know how I'm doing with the time. Maybe I'll skip this slide if you don't mind, and if we have time, then we come back to this later. One remark is, as I said, the exactness in this form of the theorem cannot be removed because we have there in one of the statements, we have exactness of the group as a condition because we have a topologically amenable action on some spectrum or some unit of sister algebra. So G must be exact if that condition holds. And also Suzuki, he proves that in general, this strong amenability is not equivalent to amenability of an action. He produces very nice examples of simple sister algebras for which even the cross product is simple and nuclear and so on. And the action is amenable, therefore, because the cross product is nuclear, but it cannot be strongly amenable because the algebra is simple, so you have no center except for the scalars. So these results shows this, and we also prove the commutative version of Matsumura's theorem. Yeah. So we extend Matsumura's theorem for the commutative version to this setting with this new definition, essentially also the same proof from the discrete case works, and proves that the weak containment in this case is indeed equivalent to amenability. In the commutative case is equivalent to weak containment and amenability. And moreover, we also relate this to some sort of amenability of the space, of the action on the space, which is not topological amenability, but measure-wise amenability. We prove that at least in the separable case that amenability is equivalent to measure-wise amenability, which means, again, going to von Neumann algebra. So one has every quasi-invariant measure, one can produce this von Neumann algebra action, and then one asks this to be amenable as a von Neumann algebra. Okay, this is Matsumura's theorem. And of course, the next question is maybe what happens if G is not exact? We use strongly the fact that the group is exact in the proof because we use this algebra CUB of G, and we use this Brodsky, Caven, Lee-Ozawa theorem that says that this action is strongly amenable, is topologically amenable, the action on the spectrum. So we use this to have some initial object with some amenability to pass amenability to the algebra. And this is the main point of the proof. And also, if the group is not exact, exact. Indeed, in general, the amenability is quite mysterious. For instance, there is no unito. One can prove that there is no unito system algebra carrying any sort of amenable action. So only non-unito system algebras can carry a amenable action. So it's difficult going to non-exact groups. But let's go to the next slide. Still, some parts of the theorem can be proved. So just after we posted our preprint in the archive, like 2 weeks later, Bearding Crane, Alex Bearding and Jason Crane, they came with a new preprint where they prove indeed that the first 2 items of our theorem can be, at least these items can be proved in general. So, and this is a very nice result, of course, because it says now we don't need exactness of the group. Amenability in our sense is von Neumann amenability from 40 years ago of Claire for this von Neumann algebra that we attach. Yeah. A very nice result. We only knew this for exact groups, and they proved extend the result to non-exact groups, and they also prove that in the commutative case, a very nice result as well, this notion of amenability that we have is exactly the topological amenability of the underlying action. So all this closes the circle of ideas and says, well, it seems that we have the correct notion of amenability that was missing. Well, now we can still ask this question from before. Yeah. So we still want to maybe ask in this Matsumura's theorem, for instance, can we do something in non-commutative case? Yeah. So we know that in the commutative case, amenability is the same as the weak containment. Can we do something in a non-commutative case? Go in this direction, we could prove at least this theorem. So we could at least characterize the weak containment in terms of some amenability-like property that we call here the commutant amenability, which is this statement that we need to look at every covariant representation. Yeah. And then in this representation, we get von Neumann algebra, which is now the commutant. This is the point. We don't look at the center. The center would be smaller. Yeah. We look at the commutant. Yeah. And then we require essentially the same sort of net as we had before for the center, but we allow more freedom here. We allow to go into the commutant, which is bigger in general than the center. And the rest is the same. We require this to converge to 1 for these bracket functions, these positive type functions that we get. Yeah? The rest is essentially the same. The main novelty here is really the difference between the commutant and the center. And this is more general concept, and this characterizes exactly the weak containment. Okay, let's go on to the next slide. It's more or less from what I said is clear that the amenability implies always the commutant amenability, because the center is always contained in this commutant. And then the question is, of course, does the converse hold? If we would be able to prove this, we would solve this open problem about the weak containment. And we could find actually examples that give a negative answer to this problem. At least in this general setting of locally compact groups, we could produce examples for the weak containment problem. So this is actually here we find some groups, some concrete groups like exact locally compact groups like PS Al2R that act on compacts. So the point here, we find some cocycles. We use representation theory of those groups to produce some, we look at the natural extension that we get from SL2R there, and then producing some cocycles. We can find some actions on compacts with this property. We really find here cocycles for which the full and the reduced twisted group system algebras are the same, and this is equivalent as saying that we have the weak containment for an action on the compacts. And this action there can never be amenable unless the group is amenable. So because the compacts are Morita equivalent to the complex numbers, so it's the same as saying that the group is amenable. Okay, this is then gives the answer to this weak containment property. So now we go one, and we also want to relate our notion of amenability with other notions existing in the literature, like by Huiexo and later for discrete groups in 1997, and also by X and Inc. together in 2002 for locally compact groups. They define the so-called approximation property for action. So actually they define it for fell bundles in general. Yeah. But in particular, this makes sense for actions, and this boils down to this condition that I write here. So the main point here is we don't need von Neumann algebras, we don't need center, we don't need commutants, we don't need to go to biduals, and don't need essentially nothing. We stay in the algebra, and we require the same type of condition, yeah. But we don't go into the center. We just require a net of compactly supported functions as before. We view it in L2. And here is the trick. We put this A, which is there, we put in the middle of this bracket. And this is the clever trick in this definition. This makes the subtle difference there, makes the whole difference. Yeah. This should now converge even in norm, not because we don't want weak topology or something like this. We are in a system algebra. So this is the most maybe simpler definition of all the definitions appearing until now, but there is this clever trick to put A in the middle there. As I said, this actually was originally defined for fell bundles, not just actions. Now I have a slide here that's also, actually I moved this slide in my new version of the slide to the end, but now let's talk about this. We also prove in this other works with Abadi Fernando, we studied also amenability for fell bundles. And there we could prove indeed that this approximation property is equivalent to amenability. Well, we extended also Claire's amenability to fell bundles and proved this result. So this in particular, of course, applies to actions, but also only for discrete groups again, okay? And also studied some equivalences and proved that all these notions are invariant under equivalence. Actually, we only proved in the first version one of the directions of the approximation property implying the amenability. Later, in the work of with Rufus and Siegfried, we proved the converse, and then using this equivalence, Morita equivalence invariance, we could then also extend to fell bundles, but now we have also a more direct proof anyway. In the new version of this paper, we have this statement. And okay, let's go to the next slide. Maybe I'm going too fast already, but anyway, so we have more time for discussions than later. And in this paper with Siegfried and Rufus again, we actually, this came a bit earlier in a paper from 2019, already published as a chapter in the AMS contemporary in the proceedings of conference by Guillermo in Buenos Aires. We came with this definition here for discrete groups because we realized that some examples by Suzuki, in these examples that I mentioned before, they had this property. So then we introduced this approximation property, which is very similar to X's approximation property, but we do it differently here. So we essentially require the existence of same sort of net, but now again, we require the same inner product conversion to 1 strictly as in the strong amenability, but now we don't go into the center, but we require that this net is almost central, so quasi-central. Yeah? In the infinity, it would be in a sense central, but we don't talk about centrality. This is the main point here. We replace the centrality condition by this almost central condition. Yeah? And it's easy to see that strong amenability implies this condition of this QAP, and QAP implies the AP. Well, if we go to the next slide, the AP already said that doesn't imply the strong amenability. So, and these examples by Suzuki, they do have the QAP, yeah, and they also amenable, we know, and in particular the IP. So the question now, how do we relate all this together? Yeah? So then we could prove, the next slide, we could prove this recently, at least now again for discrete groups. We could prove that all these notions are equivalent in the discrete case. So QAP, AP, amenability, they all are equivalent. So this closes the circle of ideas and says, well, at least if we consider these notions, they all fit together, and it seems that amenability is, as we define, seems to be the correct notion. And indeed, so in the even more recent paper by Ozawa and Suzuki, they extend this theorem to locally compact groups. So now we know that all these notions are equivalent even for locally compact groups. Yeah. And what also motivated us in this QAP is that in a previous work by Suzuki, he studies, he classifies or tries to classify actions of discrete groups. In the classification theory, this QAP was considered, and now we know many different characterizations of this QAP. So this becomes more important also because of that result. And I think this was the last slide. So thank you for the attention. This is what I had to say.
Thank you. So, are there any questions?
Well, I have one sort of a it's a comment, and just to check that I understand things correctly. So somehow, what seems to be the case is that the notion of amenability that you have described. Okay, you have counterexamples coming from SL2C of the equivalence with the weak containment property. On the other hand, if I understood correctly, this amenability is equivalent to the weak containment when you take bimodules. In other words, when you take the max tensor product of the sister algebra by the opposite sister algebra and you look at the corresponding action. I understood correctly this, I think.
Yeah, that's true.
So I liked particularly the other notion that you introduced of the commutant amenability because of its equivalence with the weak containment. and because of the fact that things don't seem to concentrate on the center anymore.
Yeah.
So my question is the following. For instance, your last theorem about this equivalence between various conditions and so on, I mean, would there be an equivalent form of it for the commutant amenability? In other words, what I am asking is that here you have many equivalent formulations. Some of them are more tractable than others, but it seems to me that the commutant amenability is a very interesting notion by itself, and that one should work on it in order to have similar equivalences.
Yeah, that's a very good question. But the point is very difficult to work with the commutant amenability. We don't have any other sort of equivalent conditions except for the fact that it's equivalent to the weak containment.
I understand, but
Yeah.
I think it's a very nice direction to explore. You know, that's
yeah. That's we try to somehow to find some other conditions, but essentially we have no other characterization except for the definition. I think we can reduce the definition a bit by saying we don't need to check for every covariant representation.
Okay.
It would be enough to check just for cyclic representations. I guess we have these results. And I think we can also prove, if I remember correctly, even if the group is not exact, that in the commutative case, this is equivalent to measure-wise amenability, and there, in the commutative case, it's actually equivalent to topological amenability because this doesn't make a difference. But now, besides that, I think we don't have any other. It's a very important question indeed. There are questions. And,
yeah, I mean, I liked your counterexample with SL2C. I mean, and the fact that you take the element in the center and you rule out the trivial representation and those which are not in the reduced one.
We also learned from these counterexamples that this notion of commutant amenability doesn't behave nicely, for instance, with respect to subgroups.
Yeah, of course, yes, sure. You mean by taking a discrete subgroup of SL2C? Yes, sure.
Yeah, exactly. And also other permanence properties maybe.
Yeah, the permanence properties are also quite important to.
Yeah. What is the other one that we discovered? Maybe I forgot, but it's really mysterious, and since it characterizes exactly the weak containment, of course, it would be very important to have a nice characterization, but it seems to be very difficult to work with this. So we don't have many. We don't have any good characterization of this, unfortunately. But maybe, yeah, in the future, maybe.
Any other questions?
I have a question. I may have missed 30 seconds of what Alcides said, and so I'm afraid I might be asking something that he already answered. But the question is, so the commutant amenability is a property that needs to be checked in every covariant representation, right? So do you have a so is there a single representation, maybe the universal representation, so that you can check it in a single representation and that being enough?
Also a good question that we investigated. I think we proved. It's a good question. I think we don't know, but maybe this universal representation could do the job.
Well, it could come from this other theorem where you had the link with.
Yeah. I need to remember. It's a good question. I think we don't know it exactly, but so we can characterize the weak containment in terms of also of injectivity of the representation of the covariant representations. And for this injectivity, we can check it only for a single faithful representation of the cross product. In the exact case, I think you could just check. No, but I think it's not clear whether this condition that we require for the net could be checked just for a single special representation. Not clear. We don't know. I think we don't know this. It's also an important question whether we could check for one. Yeah, we know that we could just check for cyclic representation. It's very difficult to work, as I said, very, very difficult to work with this commutant amenability. It's very intriguing.
So are there any other questions? If not, I have a small general question. I was under the impression that one motivation for this study of exactness, amenability, etc., had to do with this problem of finding, I mean, the right formulation or the tensor, like the correct tensor product for the bound conjecture with coefficients. Does this, would you elaborate on this, whether this is somehow related or not?
Yes, so that's related to what I just said before. So actually, we started this project on amenability when we were investigating one of these exotic cross products, the so-called maximal injective product. As we still don't know whether it's the same as this other minimal exact cross product, which is used for the new bound conjecture. And but we found out that this other cross product has a lot to do with the amenability. As I said before, we could characterize, for instance, the weak containment in terms of this this new cross product. And we have, for instance, a theorem, Matsumura's version for non-exact groups, but we replace the reduced cross product by this two cross products. So we have matsumuras. One can ask what happens. I didn't want to add more slides to the talk, but I had this in a previous version where we have a theorem that proves Matsumura's theorem for non-exact groups and commutative algebras, say, but we replace the reduced cross product by this new cross product, this maximal injective cross product, and ask it to be the same to the maximal one. And this isn't, we don't know whether it's equivalent to amenability, but we know that it's equivalent to another notion which is related to amenability, which we call the WEP, the G-equivariant expectation property, which is related to injectivity as well. So all this came from the discovery of this cross product, and then at some point we said, "Whoa! It seems that equality. We wanted to investigate when this new cross product is equal to the maximal one or reduced, and then we came to this point of amenability, you know, and then this was the time when this started." And this became an interesting subject in its own, and then we forgot the cross product, a lot of cross product.
Okay, so are there any more questions?
I think in the chat, maybe some, no.
Maybe in the chat.
The chat used to thank you and so on, I think, isn't?
Yeah, no, I don't see, I don't have any.
Maybe I was
open
very beginning. I think it's the other way around. Yeah, we contain it. The trivial representation is weakly contained. Yeah, I think Jonathan asked this very beginning. I think it was a mistake. Yeah, thank you. And sorry for
Okay.
the slides problem, and I don't know what happened that I could not share.
Okay, so if there are no more questions, I propose we thank Alcides again, and
Thank
see
you.
you next Friday, I guess.